Place a compass near an ordinary wire and nothing happens. Now switch on a current in that wire, and the compass needle swings. That tiny twitch is a huge idea. An electric current creates magnetism. In this final physics chapter, we'll see how a current makes a magnetic field, how a field then pushes a current to spin an electric motor, and how the electricity in your home is wired to be safe. We'll build every piece from scratch. Start with the field itself. A magnetic field is the region around a magnet or a current where its magnetic force can be felt. It has a size and a direction, so it's a vector. To picture it, we draw magnetic field lines. Remember 4 things about them. Outside a magnet, the lines run from the North Pole to the South Pole. They are closed loops, continuing through the magnet from south back to north. They never cross because 2 lines crossing would mean 2 field directions at one point, which is impossible. And where the lines are crowded close together, the field is stronger. Why would a current have a field at all? A scientist named Ørsted noticed a compass deflect near a current-carrying wire, proving that current produces magnetism. Around a long, straight wire, the field lines are circles, one inside the other, centered on the wire. The field is stronger close to the wire and stronger if the current is bigger. To get the direction, use the right-hand thumb rule. Grip the wire in your right hand with the thumb pointing along the current. Your curled fingers then point the way the circular field lines go. Bend that wire into a circular loop, and the little circles of field add together along the axis, giving a much stronger field through the middle. Now stack many loops into a long coil called a solenoid. Inside a solenoid, the field is uniform and points straight along the axis. And the whole coil behaves exactly like a bar magnet, with a north and a south end. Slide a soft iron rod inside, and the field becomes powerful. That is an electromagnet, and it switches off the instant the current stops. Here's the beautiful reverse. We saw a current create a field. Now a field pushes back on a current. Place a current-carrying wire inside a magnetic field, and the wire feels a force. The force is largest when the current flows at 90 degrees to the field, and it grows with both a bigger current and a stronger field. So electricity makes magnetism, and magnetism pushes electricity. The two are deeply linked. Which way does that push point? Use Fleming's left-hand rule. Hold the thumb, the first finger, and the middle finger of your left hand all at right angles. The first finger points along the field, the second or center finger points along the current, and then the thumb shows the thrust, the force on the wire. Field, current, thrust on first finger, center finger, thumb. The force is always at right angles to both the current and the field. This force is what spins an electric motor. A rectangular coil sits in a magnetic field. Current goes up one side of the coil and down the other, so by Fleming's left-hand rule, the 2 sides feel forces in opposite directions. One pushed up, one pushed down. That couple turns the coil. The clever part is the split ring, the commutator. Every half-turn, it swaps which way the current enters the coil, so the push keeps acting the same way round and the coil spins continuously. An electric motor turns electrical energy into rotation. Now the electricity that reaches your home and how it's made safe. Indian main supply is about 220 volts. It comes on 3 wires. The live wire with red or brown insulation is at high potential. The neutral wire, black or blue, completes the circuit. And the earth wire, colored green, is a safety wire connected to a metal plate buried in the ground. The potential difference between live and neutral drives the current, and all the appliances in the house are connected in parallel, so each gets the full voltage and can be switched on its own. 2 dangers, 2 protections. A short circuit happens when the live and neutral wires touch directly. Resistance drops to almost nothing, so a huge current rushes through. Overloading happens when too many appliances draw more current than the wires can safely carry. Both make the wires dangerously hot. The fuse is the guard, a thin wire placed in the live line that melts and breaks the circuit the moment the current gets too high. The earth wire is the second guard. It connects the metal body of an appliance to the ground, so if a live wire touches the casing, the current escapes safely to earth instead of through you. Let's lock in the rules. Question: in an electric motor, which rule gives the direction of the force that turns the coil? The coil carries a current and sits in a field, and we want the force the thrust. So we use Fleming's left-hand rule. And the part that reverses the current every half turn to keep it spinning is the split ring, the commutator. Keep left hand for the motor's force. We save the right hand for the next idea, generators. Your turn. The question's on screen. Pause if you like, but try it first. 10 seconds. Go. The fuse always goes in the live wire, and it protects the circuit by melting when the current becomes too large, breaking the circuit before the wiring overheats. So the correct answer is the live wire, option A. And that's the whole chapter. A current makes a magnetic field. The right-hand thumb rule gives its direction. A field pushes a current by Fleming's left-hand rule to spin a motor, and home wiring stays safe with the live, neutral, and earth wires plus the fuse. That also completes Class 10 Physics. Free notes with 60 practice questions are in the description. Subscribe to Clarix and keep going. You've got this.